Welcome. So this next chapter is on linear momentum and collision. So there's two bits to it. There's this linear momentum bit and there's the collisions bit. And I'm going to skip through it so you can see it. So basically we start off talking about linear momentum. Linear momentum is something which is very abstract. It is mass times velocity. And I don't believe most of us would invent it. It comes out because we need it. In a collision, all of physics, all of engineering is about equations. When there's an equation, something before equals something after. So you look at something like a collision, you say what before equals what's after. And you could say energy, because energy is neither created nor destroyed. But remember that once you get thermal energy, it goes out of the mechanical system. So it might not be destroyed, but it's not available to you anymore. So that's not particularly a good thing. So you go, what is maintained throughout the collision? And it turns out the thing that's maintained throughout the collision is this thing called momentum. And it's not intuitively obvious to me that I would recognize that, but that's what is maintained. So we have this thing called momentum. To give you an idea, momentum, a bullet coming at me is about the same as a big bus rolling towards me. Are they equivalent? Do I get hurt by a big bus rolling towards me as a bullet coming towards me? Well, I get hurt in different ways, don't I? I can get hit by the bus and bounce off. Bullet, it goes into me and does a lot of damage. But they're, can be the same momentum depending on their mass and velocity. So it's kind of not intuitive, but it kind of works. We can relate linear momentum with a force, and we can relate linear momentum with a thing called impulse. Impulse is how long the force is applied for. We end up with the impulse momentum theorem. And then we take that and we apply it to collisions. And at the very end, there's this bit on centre of mass. And I think it depends on, different books have that centre of mass in different chapters. So you might have a different book and it might be in a different chapter because it tends to get moved around because it's a little thing you need, but it can be the end of one chapter or the beginning of the next. Linear momentum. Momentum's a vector. It's a scalar times the vector velocity. So linear momentum is scalar mass times vector velocity. So we can say, what is the momentum of a 3 kilogram? Let's get a pen. What is the momentum of a 3 kilogram block traveling at 4 meters per second in a negative direction? So that's minus 4. So you would say, P is equal to mv. For a straight line, we'd say P is equal to the 3 times the minus 4. So my momentum equals minus 12 meters per second. Sorry, kilograms meters per second. So that's fair enough. But remember, momentum is a vector, so it lends itself to ijk. So here I have my block. That's 5 kilograms. And the velocity is 3I plus 2j minus 4k meters per second. And I would say momentum is equal to mass times velocity. So I would go, my vector momentum is equal to 5 times 3I plus 2j minus 4k. So P is equal to 15I plus 10j minus 20k kilogram meters per second. Cool. So it's just mass times velocity. Well, let's say that I differentiate my momentum in time. Let's say momentum is changing in time. I say dp by dt is equal to d by dt of mv. Well, m's a constant, so dp by dt is equal to m times dv by dt. dv by dt is a. I know that, F equals ma. So rather than saying the sum of the forces equals ma, I can say the sum of the forces equals dp by dt. And going back to what we said before about the people who do the work write it down one way and then over time it tends to get smoothed out by educators. Newton never wrote down F equals ma. This is his second law. I never wrote it down. He wrote down F equals dp by dt. So this is a different approach. He thought in terms of momentum and changes of momentum in time. An 18 Newton force is applied to a particle. Here's my particle. The force acts in a positive x direction, so this is 18 newtons. The particle is initially at rest, vi equals 0 meters per second. What is the momentum of the particle at t equals 6 seconds, so somewhere down here at delta t equals 6 seconds. We have the particle. We still have the 18 Newton force on it, and I want to know what my Vf is. What is the momentum of the particle? I'm sorry. I want to know what my Pf equals. So let's have a look. My force is equal to dp by dt, which equals delta p by delta t, which equals P final minus P initial over delta t. So that means that my 18 newtons must equal my P final, which is what I want, minus my P initial. If my velocity is 0, then my initial momentum is 0. So that's 0 over delta t is 6 seconds. So that means that my P final must equal 18 times 6, which equals 60 and 48, 108. 108 kilograms meters per second. So just playing with that relationship. It's just we're playing with that relationship. A force acts is applied to a particle. The particle's initial momentum of that. What is the momentum of the particle at t equals 5 seconds? So again, visualization. I have a force 3I plus 2J plus 4K newtons. And particle's initial momentum, Pi is equal to 1I minus 6J plus 7K kilograms meters per second. Can I just pause for a second? Do you know the direction that the particle is moving? Is it moving in the same direction as the force or the same direction as the momentum? What do you think? Remember what momentum is by definition. What's momentum by definition? It's the mass by what? Ma is force. Momentum is your mass times your velocity. Look back at your notes, it's in there. Your velocity tells you the direction of travel. So your momentum is in your direction of travel. You've got a force pushing you to the side, so what's going to happen is you're going to kind of go duck, 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 duck like that, and you're going to have a momentum in that direction because your velocity is going to change. That's P final. That delta t is equal to 5 seconds. So we say, what did we say? We said F is equal to dp by dt, good old Newton, which equals delta p by delta t, which equals P final minus P initial over delta t. So my force, so what do I want to find? I want to find my P final. Is that what it's asking? Yeah. P final is equal to force times delta t minus plus P initial. Plus P initial because that was a minus sign there. So it goes to the other side and becomes a positive sign. So that means that my P final is equal to my force, which is 3I plus 2J plus 4K times my time. My time interval is 5 seconds, plus my initial momentum, 1I minus 6J plus 7K. Let's do a little grid to get the numbers right. Whenever you get these guys and you want to get your numbers right, just do it like this. So we're going to say F delta T is going to be 3, 2, and 15, 10, and 20. I'm just multiplying those two guys out. Added to, and what was my initial momentum? P initial. So that's going to be 1 minus 6 and 7. So that's going to be 16I plus 4J plus 27K, and that's going to be kilogram meters per second. So there's my answer. 16 plus 4, 27, it's that guy. So we can play with these things. Impulse momentum. If I apply a force, I have an MA. But if my A doesn't last for very long, I don't get much change. It's the change in velocity per second. So not very many seconds, not much change in velocity. I need a way of characterizing how long I apply an acceleration for, which is the same as how long I apply a force for. So let's call the product of force times the duration for which the force is applied impulse. So if I push for a long time, I get more impulse. If I push for a short time, less impulse. If I push with a big force, more impulse. Push with a little force, less impulse. So I'll say my impulse is defined as the sum, the integral, of the force times the period of time that the force acts. Integral of F dt. And if I remember that the sum of the forces equals ma, which equals dp by dt, and I put these guys together, my impulse equals dp by dt integrated with respect to time. Well, the integral of dp by dt equals dp, delta p. So my impulse equals my change in momentum. Imp equals change in momentum. Force equaled time rate of change of momentum. F is equal to dp by dt. I is equal to delta p. They're not the same, but they're similar. And people get them confused all the time. So the way you avoid that is you put them side by side and you make sure you can distinguish between the two. What's similar, what's different. Don't get those two confused. This is the impulse momentum theorem. Impulse is the area under a force versus time graph. If it's a variable force in time, you get variable shape. And I can represent that as an average force applied for the entire time, in which case I have my average force times my duration. As long as the areas are the same, it's the same effect. In truth, when I kick something, I have a little force at the beginning, and then as I compress the ball, I have a bigger force. Then as the ball springs away, I get a smaller force. So this kind of weird shaped thing is the realistic force versus time relationship, although we tend to simplify it. Next time, we're going to apply these things to collisions. So we'll work out how to do impulse momentum, and we'll apply it to collisions, and we'll end up with some formalism for how we do collisions. So I will see you guys in lab, but I'll see you on this